Hello and welcome to this Python tutorial. Alright, so we have very exciting tutorials ahead of us. We are going to start by creating the architecture of the neural network. That is, we will make the neural network that will be at the heart of our AI and that will return the action to play at each time t. So let's do this. So since we want our neural network to be an object, we're going to make a class, and that's because it's much more convenient. You know, a class is the model of something we want to build. We want to build a neural network, and we need to make some kind of instructions which will all be contained in a class. And in this class, we're going to make two functions. First, the init function, which is the function that comes up all the time when making a class, and that basically defines the variable of your object, that is the neural network. You know, the variables attached to the object as opposed to the global variables. And so this is in this init function that will define the architecture of the neural network. You know, defining the input layer, which will be composed of 5 input neurons because we have 5 dimensions for the encoded vector of input state. Then we will define some hidden layers. Maybe we'll start with one hidden layer, and then you will be welcome to try some other architectures of the neural network. And then of course we will end up with the output layer that will contain the possible actions that we can play at each time. So that's exactly what we'll do in this init function. And then we will make another function still inside the class, which will be the forward function, and that will be the function that will activate the neurons in the neural network, you know, that will activate the signals. And so we will use a rectifier activation function because of course we're dealing with a purely nonlinear problem, and this rectifier function breaks the linearity. But mostly we're making this forward function to return the Q values, which are the outputs of the neural network. But we have one Q value for each action, and later on we will be returning the final action by either taking the max of the Q values or using a softmax method. We will see that afterwards. So in this tutorial we're going to start by implementing the init function, and in the next one we will be implementing the forward function. So let's do this. First we need to introduce our class. So we start with class, then we give a name to our class, which is, well, we can call it network. And then in this network class, I'm going to use an object programming technique, which is called inheritance. And that is just to inherit from all the tools of a parent class. So our network class that we're about to make is a child class of a larger class, which is nn.module. So that's just to inherit from all the tools of this module class, which are of course the tools to implement a neural network. So that's a very powerful and efficient trick in object-oriented programming. That's called inheritance, and right now we are inheriting from this module parent class. All right, and now we're ready to go inside the class. So I'm pressing enter, twice actually, because we'll be making two functions, and we're starting with the init function. So the init function, we have to name it this way with 2 underscores, then init, and then again 2 underscores. That's just Python syntax. That is just how we have to do it. And then we need to input the arguments. So we have 3 arguments. The first one is a compulsory argument. That is actually self. And self, there is no mystery about it, that refers to the object that will be created from this class that we're about to make. You know, we're making this class. It's like some instructions, some model of this neural network we want to build. And then once the class is ready, we can make as many neural networks as we want, and each of these neural networks will be some object of this class. And since we'll be using the object for some other purposes, we need to spot what are the variables of the object. And to spot this, we are using this self here to specify that we're referring to the object. So whenever I want to use a variable from my object, I will use self before the variable to specify that this is a variable of the object. Alright, so that's the first argument, and then we have 2 other arguments, which are of course the number of input neurons and the number of output neurons. So the number of input neurons, we're going to call it input size, and that's actually 5, because our input vectors have 5 dimensions, the 3 signals plus orientation plus minus orientation. That's our vectors of encoded values that describe one state of the environment. These 5 values are enough to describe a state of the environment. We could have thought of less values or more values, But that's what I tried, and it actually makes sense because we actually need one signal from the left, one in front of us, and one at the right. You know, when we're driving a car. We could have gone for a 360 signal, you know, like the signals at the top of the Google cars, but we can totally self-drive with 3 sensors. And then we have this orientation and minus orientation to, you know, keep track of the goal that we're trying to reach. And then we have, of course, the output neurons of our neural network, which correspond to the actions, and we have 3 possible actions, going left, going straight, or going right, and therefore I'm going to call it NB action, and there will be 3 of them. Alright, but so far we only have to give names to the input, and then we'll use these variables to do the computations inside the neural network. Alright, then I'm going to start by using another PyTorch trick. This trick is the super function. That's a function that actually inherits from the NN module. So that's why we had to use inheritance to inherit of the module tool. This is the first tool we use. And so basically, we're only using this super trick, this super function, to be able to use the tools of module. So that's much more efficient. And inside this super function, I just need to specify first the network. So that's our network child class, you know, because this is inheriting from the module parent class, and then our object. And then I'm just adding dot and our init function, like this, exactly how we named it. All right, so that's just a trick. That's just to use all the tools of NN.module. Then we can move on to the next step, which is to specify the input layer. So basically what I have to do is introduce a new variable that will be attached to the object, and this variable will contain the number of input neurons. So not to be confused with input size is the argument of the init function, but that's not the variable that is attached to the object yet. The variable that is attached to the object, well, as I just mentioned, we need to specify that it is instead attached to the object, so we use a self dot, and now we give a name to this first variable attached to the object. And so we can simply give the same name as the input. We can call it input size. And we will say it is equal to the argument of the init function, that is input size. All right, so each time I'm creating an object from the network class and I'm specifying the input size, like for example, I'm inputting 5, there will be a 5 here, and therefore the input size variable of our object will have the value of 5, because this input size here will be 5. And therefore our neural network will have 5 input neurons in the input layer. All right, and then that's the same for the other variable that we want to attach to our object. And as you might have guessed, this is going to be a variable for the number of output neurons. And so same, we take our object, self, and then we give a name to this second variable of the object. We're going to call it NB action. And this will be equal to this argument here, giving the number of actions, that is the number of output neurons. And so we set it equal to NB action. So actually, NB action will be equal to 3. Therefore, the variable NB action attached to our object, to our network, will get the value of 3. Actually, we can see a warning here. It says undefined name NN. Well, that's because here we use the NN shortcut, and we need to use the shortcut here, NN, for our torch.nn module, and then it will disappear. Here we go, perfect. Right now we have no warnings. All the warnings here are just to specify that what we import is not yet used, but that's okay, we will be using them afterwards. All right, then we have another 2 variables we want to define for our object, and this will be the full connections. The full connections between the different layers of our neural network. So since right now we want to make a neural network composed of only one hidden layer, well, there will be 2 full connections. There will be one first full connection between the input layer and the hidden layer, and one second full connection between the hidden layer and the output layer. So let's start with the first full connection. We're going to call it FC1, and again, I use self here to specify that FC1 is a variable of my object. So self.fc1, which will be equal to, and now we use the NN module, and we're going to use a function called linear, and that's exactly to make this full connection between the neurons of the input layer to the neurons of the hidden layer. And what do I mean by full connection? That means that all the neurons of the input layer will all be connected to all the neurons of the hidden layer. And so to make this full connection, we use this linear function to which we need to input some argument. And as you can see, these arguments are in features, so that is the number of neurons of the first layer we want to connect. Then the out features, that is the number of neurons of the second layer we want to connect, that is the layer at the right, that is the hidden layer, and bias equals true. So bias equals true, we will keep the default value. That's in order to have a bias, and not only some weights attached to the neurons, we'll have the weight and one bias for each layer. And so, well, let's see what we need to input. So the first argument in features is the number of input neurons in the input layer. And so what is it? Well, that's actually input size. That's the argument of our init function, which later will be equal to 5, the 3 signals, orientation and minus orientation. So here we go. We input the first argument, input size, and then the second argument is out features. That is the number of neurons we want to have in the second layer that will be fully connected to the first layer. And so now the question is, how many neurons do we want in this hidden layer? Well, I did a lot of parameter tuning, I did a lot of experimenting. That's what we do in AI, or that's what we do in deep learning in general. We do a lot of experimenting to see what would be the best neural network for our specific problem. And so I tried many values, and I ended up choosing 30 neurons in a hidden layer, and you will see that with this number we will get some pretty good results. But then feel free to change the architecture of the neural network, feel free to play with it. You can not only change the number of hidden neurons in the hidden layer, but also you can add some more layers so that maybe you get an even better car. But 30 hidden neurons will get us a good neural network and a good car. So that's what we go for, and there we go, we have our first full connection ready. With this linear function, we make the full connection between the input layer and the hidden layer. And now, time to make the second full connection, that is the full connection between the hidden layer and the output layer. So there we go. We're going to call this second full connection FC2. There we go. And still this is a variable from our object, so I'm using self here. And then again we use, well, actually we can copy this because we're going to use the NN module and then the linear function. But then we need to change the arguments, of course. First, that's the same. First is the number of neurons we want to have in the first layer of the full connection. So that's the hidden layer, and therefore that is 30. And then second argument is the number of neurons in the second layer of the full connection, and that corresponds to the output layer, and the output layer has NB action neurons, which later will be 3, because we have 3 possible actions. But so far, we have to use the names we defined, that is the names of the argument of the init function, and therefore we input here NB action. And there we go. First of all, our 2 full connections is ready, and second of all, our init function is ready. So that's what will initialize our object whenever we create an object from the network class. And so as soon as we create an object, well, all these variables, the 4 variables here, input size, NB action, FC1 and FC2, will be defined, and that's how we'll get the architecture of our neural network for each object that we create. Each object will correspond to a neural network of 5 input neurons, 30 hidden neurons, and 3 output neurons. So there we go. We are done with this first init function, and now we can move on to the second function, which is the forward function, and that will be used to activate the neurons in the neural network using the rectifier activation function, and mostly to eventually return the Q values, which are the outputs of our neural network. So I can't wait to do this in the next tutorial, and until then, enjoy AI!